Hi, in this video we look at an introduction to imaginary numbers. So for a very long time, mathematicians thought there's no real solutions to this equation. X squared is equal to -1. And there aren't any real solutions to this equation because if I take a real number and I square it, I'm going to get a positive number, always. So a mathematician in the 1700s came along. His name was Leonard Euler, and he said, let's introduce an object. Let's imagine an object, I, such that when I square I get -1. Now he defined I to be, he said, let's let I be equal to the square root of -1. Now the introduction of such an object has led to really profound and a lot of really useful results in math. So this is an incredibly useful thing to do because it allows us to solve a lot of different problems in higher level math and just in general in math. So the introduction of this object, well, if we're going to introduce something like this in math, we have to make sure that it's consistent with our other rules of arithmetic and whatnot. So first off, if I square I should get -1 because squaring is the inverse operation of taking the square root. So when I square I should get -1. The other thing is that this number I is actually in a different set of numbers than the imaginary numbers. It's part of the imaginary number system. So imagine that, we have the, well, let's see here. Normally we have the real number system, and within the real number system we have the irrational numbers, we have the rational numbers, we have the integers like 1, 2, 3, 4, 5, 6, 7, 8, 0, -1, -2, -3, -4. All of those numbers are contained in the real number system. We also have, so now we're introducing this other set of numbers, the imaginary numbers. So the imaginary number system is all of the numbers that have I in them, and they're distinct from the real numbers. If I want to get the imaginary numbers, what values are in the imaginary number system, I can simply multiply the real number system by I, and I'll get all of the imaginary numbers. So there's exactly the same number of elements, or the same number of numbers in the imaginary numbers that there are in the real numbers. Because if I take a real number such as I don't know, like 6, and I multiply it by I, well, I'll get, there's a corresponding number for 6 in the imaginary number system. I just have to multiply the number in the real system by I, and I'll get a corresponding number in the imaginary number system. Now, just like in the real number system where I can count, in terms of integer values, I can count like 1, 2, 3, 4, etc., etc. There are consecutive numbers in the imaginary number system. Like I would have 1i, I would have 2i, I'd have 3i, and 4i, and 4i and 5i. There's also negative imaginary numbers as well. So I could have, -1i, -2i, -3i, and so forth. And as well as numbers that are between -1 and -2i, just like in the real number system. So I've got all the numbers between -1i and -2i. So literally, we just can take the real number set and multiply it by I, and I'll get the whole imaginary number set. So let's think about what other operations we have in the real number system. Well, I know that first off, I know that in my imaginary number system, my imaginary number system has to be consistent with the arithmetic operations that I already have in the real number system. So let's say I have like the square root of -x. Well, based on how I simplify radicals in the real number system, I know that this should be, I can rewrite this as the square root of -1 times the square root of x. Now let's say that x here is greater than or equal to 0, and x is a real number. So x is an element of the real numbers. Well, based on how I've defined the square root of -1, I said that the square root of -1 was just I. So I have that the square root of -x is just equal to the root of x times I. And I can use this property to simplify square roots of negative numbers. We can reduce radicals involving negative numbers. So we'll look at how to do that in the next video.